Hey everyone, in this video I'm just going to do a quick walkthrough here on how to do some Faraday's Law problems. So when we talk about Faraday's Law problem, what we're really doing here is we're working electrolytic cells. And electrolytic cells, as we learned in the previous video, these are your non-spontaneous, so your voltage would normally be negative, therefore non-spontaneous, and so we have to force these reactions to actually take place. So even though they're non-spontaneous, we're turning them into an electrolytic cell by supplying outside voltage, so an external voltage source, to kind of pump this reaction full of electrons and force it to go, even though it doesn't want to. And so the most common application of this probably is electroplating. So this is the process by which they put chrome on car bumpers, if they get chromed out bumpers, or if you get galvanized metal, galvanized steel, like in your nails or your fence posts or things like that. They would put an electrode in solution and with an ion of that particular metal. Let's just say you put in an iron electrode with zinc nitrate solution, pump it full of electricity, and the zinc will plate out on the iron. So anyway, that's the process we've got going here. And really, this is just one big, gigantic dimensional analysis problem. So a couple of things here. We do have one of our constants to use, F. Remember that from the Niffy equation. That stands for Faraday's constant. And that's 96,500. We use slightly different. We use joules per volt mole in the negative Niffy equation. For this stuff, we're going to use coulombs per mole of electrons. So that's still your mole. Excuse me. And so this coulomb is just the SI unit of measurement for charge. And then the other piece of information we want to share here is that current, the SI unit for current is amps, capital A. And an amp is just coulomb per amount of time, so coulombs per second. So we're going to make use of that. Get right into problem number one here. So you'll see this is a pretty straightforward problem. How long in minutes must a current of 5 amps be applied to a solution of silver ions to produce 10.5 grams of silver metal? So I guess first things first here, let's look at the reaction. We're taking silver, we're going to pump electricity into it, so there's my electrons, and we're reducing it to silver metal. So a very simple reduction here. We don't care what's happening at the anode, this is just, we're plating, this is all we're doing. And so when you work these problems, you have kind of on one end of the seesaw, like grams mass amount of the metal, and then on the other end of the seesaw you have time, and then it's all the stuff in the middle, these little tools to get from mass to time and backwards that I'm going to show you how to do in this video. So we're going to start with 10.5 grams of silver. Okay, and like anything else in chemistry, we got to go to moles. Keep your descriptors on these dimensional analysis problems so that you know you're dealing with moles of silver here. Because here's a very important step in this. I'm now going to convert out of moles of silver, and I need to know about moles of electrons, because again, amps is a current, which is the flow of electrons. Not the flow of atoms, the flow of electrons. So this is technically my stoich step right here. And that's why I need my reaction. So I can see here 1 mole of silver requires 1 mole of electrons. And so my unit now is currently moles of electrons. Now the other new tool that we're going to use here is that Faraday's constant. We know that for every 1 mole of electrons, we're going to need 96,500 coulombs of charge. Okay, so that's the total, sort of the total amount now of electrical charge we need. And now we're going to see how much time that takes. We're going to be using the 5 amps. I need to know how much charge per second or for how many total seconds. So that's going to be 5 coulombs per second. That's the application of my current. All right, so one more thing to this problem. Sometimes we may be able to stop there, but it did say how long in minutes. So this is just a little extra add-on here to go from seconds to minutes. 1 minute is 60 seconds. And so we worked that out, round it 2 sig figs, 31 minutes is how long you have to pump 5 amps into this solution. All right, let's just keep going here. Number 2, we have an electrolytic cell. We're going to be pumping 0.25 amps through a solution of a chloride of iron, and we're going to produce iron solid and chlorine. So that kind of tells us what we have going on here. It wants the anode. So we know what's happening at the anode. Think about what's happening to yourself. Is it the iron or the chlorine that's going to be happening here? If you said the chlorine, you were correct. The anode is oxidation. So if I have a solution of a chloride of iron, we know that the chloride is currently chloride negative charge, and we're going to oxidize that to Cl2. Now, I can look at that real quick and say I need to balance. So there's going to be 2 involved here, which means I need 2 electrons. So that's the anode reaction for this. It doesn't really ask right now what the cathode reaction is. We're going to be using it in part B. So let's go ahead and get that cathode reaction. So what's going to happen here is I have some chloride. I don't know if this is iron 2 chloride, iron 3 chloride, iron 4, whatever. So this is going to be Fe plus a charge of X. I don't know what it is, but I know that it's going to reduce to iron metal. It did tell me that. So how many electrons is that going to take, or going to absorb, I guess? Well, it's going to be X. So X number of electrons. So let's look at part B now. When the cell operates for 2 hours, 0.521 grams of iron is deposited at 1 electrode. Determine the formula of chloride. So it wants to know what this charge is on the iron, so I can get the ultimate formula. All right, well, we can do that. The only problem with that not knowing is I don't know my stoichiometry. I don't know how many moles of electrons. Is it 2? Is it something else? You know, I don't really know. I don't know the middle part here. So what I'm going to do in this problem is I'm going to work from both ends and sort of tie a knot in the middle to bring the whole thing together. Watch this. So we're going to take 0.521 grams of iron, and we're going to convert it to moles. So 1 mole of iron from the periodic table is 55.85 grams. Left my 5 off there. All right, and that gives me 0.00933 moles of iron. All right, so that's coming from one end. Now let's go and start on the time end and go backwards. So we're going to take 2 hours, and I want to convert that into seconds because that's what amperage is in. So that's hours to seconds. Now I'm going to use my amperage, 0.25 coulombs per second. So hours are gone, seconds are gone. Now I'm in coulombs. Now I'm going to convert out of coulombs and into electrons. So this is the Faraday's constant, 96,500 for every 1 mole of electrons. And this is 0.0187 moles of electrons. All right, so now what I did, the way I see it, I know there's more than one way to work this problem. I've had students in the past do it a completely different way. But the way I see it is I want to look at how many moles of electrons for every mole of iron that gets reacted. So I'm just going to do a ratio here. 0.0187 moles of electrons over 0.00933 moles of iron. And lo and behold, that comes out to be right at 2. It's like 1.99, so it's not exactly 2, but it's really close to 2 because of the rounding. So that means if I can go all the way back to my cathode ray half reaction, or sorry, my cathode half reaction here, that means X is 2. So this salt was FeCl2, iron plus 2, iron 2 chloride. Knowing that the reaction for this cell floating around all this time was iron 2, the 2 chlorides, we reduced the iron and oxidized the chlorine. Now we don't always use gas for this, or use solids for this. We could also use gases. So let me back this up and keep the camera giving us something to see here. It's late at night. I could have been better prepared, but this is what you get. All right, so calculate the amount of current that would produce chlorine gas at the rate of 3 grams per hour. Well, that's where we're going to start here, 3 grams per hour. And again, hours aren't that helpful to me because we're using amps. So I want to get out of hours and go to seconds. All right, so that gets rid of that. Now I'm in grams per second. It wants to know current. So my ultimate unit here needs to be coulombs per second. So I'm going to leave this denominator alone here, and I'm going to turn my attention on getting grams into coulombs. So let's start that conversion process. Let's put grams on the bottom. We know we need to get to moles. Okay. 1 mole of Cl2 diatomic is 71 grams. All right, so that takes care of the mass. Then stoichiometry. From the balanced equation up here, we didn't really write N out, but we hopefully can see that N is 2 here. We figured that out for part B. So for every mole of chlorine, there needs to be 2 moles of electrons. Gets rid of chlorine. And then finally, I can get rid of my moles and get into charge, and that's the Faraday's constant, 96,500 coulombs per mole. Run all this through the calculator, and we're going to get 2.27 amps for coulombs per second. Very straightforward stuff. It's just a gigantic unit conversion. Alright, so let's just keep going here. You can stop the video at any time when you think you got it. Some of you like to see more examples than others, so I want to make sure I provide everybody with what they need. So I'm going to move on to number 3 here. A steady current of 1 amp is passed through an electrolytic cell containing a solution of silver nitrate and having a silver anode and a platinum cathode until 1.54 grams of silver is deposited. Okay, so don't be confused on the reading of this. So what's happening here is that the platinum electrode is inert, but it is the cathode. So that's where, from this solution of Ag positive and nitrate swimming around, that as we pump electrons into this solution, we're going to make silver metal. And that's going to happen at the platinum electrode. And it's just going to coat the platinum, and when we're done, we can scrape it off, or, or we just, in some cases it sticks and you're not able to remove it, but when it's platinum, we can usually remove it. All right, how long does it take the current to obtain this deposit? Well, we got 1.54 grams. And by the way, if you want to stop the video, run through this conversion, see if you get it right. I suggest you do that. So I'm going to go ahead and let you hit pause now if you want to stop and run through this, and then I'm just going to work through it and just cough and just continue to cough. All right. Let's check your work. So we're going to go from grams to moles. So mole conversion there gets rid of grams. Our stoic. And didn't really write the equation too clearly, so just in case, it's very similar to the first problem we worked. We're just going to reduce some silver, so it's a 1-to-1 stoichiometry. And then let's throw up our Faraday's conversion and our amperage, which is just in terms of coulombs per second, just 1 coulomb per second. And rounding it, I rounded it to 4 sig figs. I realized later I should have done 3. So I got 1377 seconds, but some of you may have gotten and rounded it a little better, 1380 seconds. All right, go. B part. What weight of the chromium will be deposited in a second cell containing 1 molar chromium-3 nitrate and having a chromium anode and a platinum cathode? So sort of the same deal here. By the same current, the same time used as the silver. So basically we're just going to change the solution up, do everything the same, and see if we can get, sort of the same amount of, well, I guess it'd be the same amount of silver. Well, maybe rephrase that. See if we can get the same amount of chromium as we did silver in the previous problem. Okay, easy for me to say. Alright, so let's do this. We're going to run it for the same amount of time. So 1380 seconds. So we're starting from the other end here because we know the time now. So let's put that current in there. This is going to be coulombs per second. 1 coulomb per second. And now it just means Faraday's constant is going to flip over. Coulombs per mole of electron. And now we need to know this reaction. This is chromium-3. So this will take 3 electrons to plate out. So we are going to have different stoichiometry here. So for every mole of chromium, it's going to take 3 moles of electrons. And then finally, moles of chromium, 52 grams per mole. So we do all that. We run the same current for the same amount of time as we did for the silver, but we only get, I'm going to be a little off here because I realized I used, for some reason I wrote my number down wrong earlier. It's going to be about this number. You may have something a little bit higher than that, maybe 0.26 or 0.27. But either way, that's all the chromium we get compared to the 1.54 for silver. And that's because it chews up more electrons. So you got to pump more, you have to pump more total charge into this one. So at the same rate of charge being introduced, you're not going to get as much out of it. Alright, last problem on this worksheet. If both electrodes were platinum in this second cell, what volume of oxygen? Alright, so this goes back to the other video we watched where if you have these inert electrodes and we're competing with the water reaction, so if this platinum is the inert electrode at the anode, then the only thing that can be oxidized here at that point is the water. So we're going to oxidize water into O2. So I'm going to write that reaction. Now, I do know I'm writing it in reduction form, but you've done enough of this, I hope, to start seeing it. So that's written in reduction form, but it's the opposite reaction, and the voltage for that one is 1.23 volts. I just wrote it down just so we can see. Alright, but the problem said we're going to run the same setup, so 1380 seconds. So we're going to pump the same current through there. We're going to use Faraday's constant in the exact same way. And now we need to look at our stoichiometry. That will be different. Moles of electrons per moles of O2. So we'll look at our half reaction here, and we can see the N is 4. So 4 electrons per mole of oxygen. And then, once all these units are canceled out, I want to convert oxygen, which is in moles, into volume. And this clue here that we're at STP, that's very helpful. Because in pre-AP we learned that 1 mole of any gas at STP is 22.4 liters. So we're going to take advantage of that. If not, you could have brought this out and used PIV inert and get the same answer. So once again, I have probably a little bit of a wrong answer here, because the number I started with, I see I wrote it down wrong. So 0.080 liters or 80 mils, and you may be just within a mil of that number because I made a slight small error. All right, well, that's Faraday's law. It's pretty straightforward. Like I said, it's just a giant unit conversion. So I hope you think that's easy and not too bad, and in a perverse way a little enjoyable. If you don't understand it or have any questions, make sure you come by and ask, and we'll get it squared away.